How did Aeroelastic Flutter cause the Tacoma Narrows Bridge collapse? Imagine a bridge that looks almost alive, twisting and swaying in the wind until it suddenly snaps. That's what happened to the Tacoma Narrows Bridge in 1940. The story is a fascinating mix of engineering design, environmental forces, and physics. It all comes down to how structures respond to wind and how their design can sometimes set the stage for failure. The collapse was mainly caused by a phenomenon called aeroelastic flutter. This is when wind forces and a structure's flexibility interact in a way that makes the structure oscillate more and more. Instead of calming down, these vibrations grow larger over time. Think of it like a swing that keeps going higher because the push keeps coming at just the right moment. When this happens to a bridge, it can cause twisting, bending, and eventually breaking apart. The Tacoma Narrows Bridge was built with a very flexible design. It had a shallow stiffening girder that was only 8 feet deep, which made it more bendable. The roadway was narrow compared to the length of the main span, and the side spans were long with cables from the main structure. These choices made the bridge more susceptible to wind forces. Unlike bridges with open trusses that let wind pass through, this bridge had a solid plate girder deck. This deck acted like an aerofoil, which is a shape that can generate lift or aerodynamic forces when wind flows over it. On the day of the collapse, winds reached about 19 meters per second, or roughly 70 kilometers per hour. These strong winds caused the bridge to start oscillating. At first, the motion was simple vertical waves, but then it turned into a twisting motion. The two halves of the bridge moved in opposite directions, creating a torsional or twisting vibration. This was triggered when a cable bent on the north side slipped, balancing the tension in the cables. That imbalance allowed the flexible girders to twist even more. As the twisting increased, the wind forces fed back into the motion, making it grow larger. This created a self-reinforcing cycle where the wind actually added energy to the oscillations instead of damping them out. This is different from resonance, where vibrations happen at a specific frequency. Aeroelastic flutter involves negative damping, meaning the wind keeps pushing the structure to oscillate more. The vortices or swirling air patterns formed in phase with the bridge's motion, giving it more energy to keep twisting. Back then, engineers did not fully understand how wind and flexible structures interacted. The design of the Tacoma Narrows Bridge did not account for these aerodynamic effects. After the collapse, wind tunnel tests and further studies showed that increasing stiffness or adding dampers could prevent flutter. Modern bridges now include features like open trusses, aerodynamic shapes, and tuned mass dampers to control these oscillations. This event taught engineers a vital lesson. Considering how wind interacts with a structure's shape and flexibility is essential. If not, even a well-designed bridge can become a victim of its environment. The Tacoma Narrows Bridge collapse remains a clear example of how design weaknesses and environmental forces can come together to cause a catastrophic failure.